So in this problem, we're going to look at 8.8 from the homework this week. I actually think that, a little bit of behind the scenes explanation, they give kind of estimates of difficulty of the problems. And this is actually ranked one of the easier problems in the book. And I think it is easy to solve mathematically, but to actually think about what's going on, it's a little bit more challenging. So you have a bracket, and you can imagine that it has these hollow collars, and it's actually slipped over that rod. And imagine that the connection between the bracket itself and the rod is pretty tight. So if this bracket doesn't weigh much, it can kind of just sit there in a stationary fashion. Of course, though, eventually when you push it down, just imagine that the bracket also has a horizontal kind of arm to it, and you're pushing down at the end of that arm. That, of course, because of the nature of friction between the material of which the rod is made and the bracket is made, you can actually counterbalance or oppose a little bit of that downward force. So when you push with P, it won't move for a second. But in addition, when you think about all of the things going on from rigid body equilibrium, you have other things going on as well. Namely, when you push P at this on that horizontal arm of the bracket at length D, that bracket is going to tend to rotate in the counterclockwise direction. So the actual normal force that the rod is exerting on the bracket is what's going to tend to kind of stop it from rotating as well. So there's a lot going on here, and just the way that you typically approach these problems is to draw a free body diagram. And once you have the free body diagram, go back to the problem description and see how much information you can actually tease out from what you're given. Because what part of what's confusing here is once we have the free body diagram, which we'll look at in a minute, and I just want to be clear that this is kind of the vertical component, and these little stubs here are the circular collars that are actually slipped over the rod. So you can imagine the rod passing purely vertical down here. Now, I think the hardest part of solving this problem is understanding where to actually draw your frictional forces, which we'll talk about here in a minute. So pretty obvious that the applied force P is applied at some distance D. That distance D is referenced kind of from the middle of the actual circular collars in the bracket, and you're told that the diameter of those collars is 0.5. So note that in the actual original drawing, they're calling point B, and I'm going to go back to the actual problem description here, is kind of a point on the bottom that's at the leftmost edge of the actual circular collar, versus point A is at the rightmost edge of the circular collar. And if you don't remember that, of course, right, this is slipped around in a circular fashion, so that frictional force is distributed across the entire contact surface between the bracket and the rod. But what is happening is if you don't apply your frictional forces at the exact points that they've shown, A and B, so A goes on the right side of the rod and B goes on the left side of the rod, you're going to have some problems setting this problem up. And I'm imagining if any of you are having problems, that's exactly what's going on. Now, the question is, well, how would you know to actually apply it there? Well, you have to kind of leverage the fact that they told you the coefficient of static friction is 0.6 at those points. So be very careful here. It looks like these are kind of drawn at the same point, but in fact, B and A are offset horizontally. B is on the left side of the rod, and A is on the right side of the rod. And if you don't draw it that way, you'll never get the actual setup correctly. So in both cases, right at the point at which we're kind of modeling the interactions of the surfaces, we'll have a normal force that's perpendicular to the surfaces and a frictional force, which is parallel. So in the case of the upper collar of the bracket, that's going to be on the right side, as I've shown. In the case of the lower collar of the bracket, it's going to be on the left side. So think about all the unknowns that we have. We have two unknowns associated with the normal force, two unknowns associated with the frictional forces. We don't know what P is, and in addition, we don't know what this distance is. That's what we're trying to determine. So we have 6 unknowns. We have 3 equations of equilibrium, and we can also apply, because we're trying to find that maximum distance D, that if we were to extend beyond that, this bracket would slip. We have 2 equations of impending motion, because we can actually assume that these frictional forces are the maximum static frictional forces that can be applied. So in terms of going back to the problem statement, that comes from the part, the bracket doesn't slip. So I think those are the 2 most challenging things about this. Obviously, if you have 6 unknowns and 5 equations, that's generally not going to be statically determinate, but what we'll see is when we actually write the equations of equilibrium, this is. So one thing you'll notice automatically that might look a little bit weird to you is frictional forces, right? We have to assume their correct direction on the free body diagram, because that equation that we have for impending motion, frictional force is proportional to the normal force, that doesn't have a sense associated with it. So we always have to be careful to assume, or correctly assume, that the directions of the frictional forces oppose impending motion. So if this bracket is being pushed down, clearly the frictional forces are pushing it up in order to stop it from moving. However, for the normal forces at the reactions, remember all the problems that we've worked up until now, we can always assume whatever direction of those forces we want on the free body diagram. And if we assume wrong, the math will work itself out. So I chose in this particular setup to naturally assume that the normal force at A is kind of pulling that bracket back to the right. and that the normal force at B is pulling it to the left. Now, you might ask, well, why would I choose to assume that? Well, if you just look at what this force P is going to do when it's applied, it's going to rotate that bracket in the counterclockwise direction. So clearly the normal force at A is the only thing that's tending to, because if we were to enforce a moment about point B, which we will in a minute, is the only thing that's tending to counterbalance that rotation. So I know that these, in fact, and another way to look at it is, if you think about summing all forces in the horizontal direction, if these aren't equal and opposite, then they both must be equal to zero. So that's why I chose to show NA going to the right. Physically, I know that it counterbalances the tendency of that force P to rotate in the counterclockwise direction. So if I sum all forces in the x direction, I have NA going right and B going left. So NA minus NB equals 0, or NA just equals NB, which, as we mentioned, shows that the normal forces are equal and opposite. If we sum all forces in the vertical direction, in the upward direction, we have the two frictional forces, which are counterbalancing that applied force P, which wants to shift this bracket in the downward direction. That tells us that those two frictional forces must sum together to BP. We know that we have an impending motion situation. We're interested in solving for the scenario where this bracket is just about to slip. So I can replace FA and FB by their the maximum frictional force expressions. Each is the coefficient of static friction times a normal force. I've just factored that out. And what this really shows me is, at the point of impending motion, since I know these NA and NB are equal based upon the sign convention that I've shown above, they're equal in magnitude and opposite in direction, I have a relationship at the point of impending motion between the applied force and the normal force. So that's kind of coming from those first two equations. In addition, if I sum all moments about point B, now this is a confusing part, because remember that your B is defined as kind of the left edge of that collar. So when I compute the tendency of force P to actually rotate in the counterclockwise direction, hopefully everyone sees that P is going to induce counterclockwise rotation, so it gets a positive sign. The magnitude of the force is P. The question is, what is that perpendicular distance? Well, note that the way that the book has kind of defined distance D, it goes from the point of application of P to the actual middle of that collar. So if you know the collar is 0.5 inches of diameter, to get back to B, which is on the left end of the edge, you have to subtract out half of that diameter, or the radius. So that's where this perpendicular distance is coming from. In addition, when we consider the tendency of the normal force to rotate it back in the clockwise direction, by our sign convention, that will be a negative rotation. The magnitude of the force is NA, and this distance is actually pretty easy to see, right? That's just going to be our 7-inch kind of height that we were quoted here. So that's where that's coming from. Probably the most confusing part of the problem is when you consider the tendency of this frictional force FA to rotate about point B. Naturally, it's going to be a counterclockwise rotation, so you know that's going to be positive. We know the force is FA, which we can replace by, since we're in impending motion, US times NA. But the question is, what's going to be the perpendicular distance? Well, the perpendicular distance is, in this case, just going to be the diameter of the collar. And the reason is, if you drop down that line of action of the force, it's kind of on the right edge of the collar. And remember, point B is on the left edge of the collar, so that distance is nothing more than the diameter. So it looks like we just are drowning in a bunch of math, right? Basically, we know that from equations 1 and 2, we have a relationship between the applied force P and the normal force. And it doesn't matter which one, because equation 1 shows us that both are equal. So the best we can do is just try to solve this for this unknown dimension D. And what you'll find is, when you try to solve this for this unknown dimension D, in the actual numerator, you have two expressions that involve that normal force NA, and in the denominator, you have the expression that involves the applied force P. But remember that you can relate NA and P. So if you factor out NA and then substitute P in terms of NA, you'll be able to cancel, and believe it or not, what you get is something that's totally determinate, just a bunch of numbers that you can plug in. And hopefully when you do that, you will find that that distance you're looking for is 5.83 inches. So again, this problem, particularly if you happen to take some inspiration from online sources where the actual setup was available, the math, in terms of writing those equations, if you know the perpendicular distances, is relatively easy. And if you don't really think about what's going on with the math and you just treat it as an algebra problem, it's not the worst thing in the world to solve. But there's a lot going on there physically that I hope you take some time to think about and really consider, and because it's a good indication of whether or not you're actually getting what you want from this course, particularly if you're going down to kind of mechanical design or civil engineering scenarios where you're going to have to think about objects in equilibrium off